Tonight, we're going to talk about the largest object ever found in the universe. In 2013, astronomers mapped a structure in deep space that spans 10 billion light-years. That's larger than a billion Milky Way galaxies lined up side by side. It's so large that by all our calculations, by every theory we have about cosmic structure formation, it simply cannot exist. There hasn't been enough time since the Big Bang for gravity to build something this enormous. And yet, there it is. And by the end of tonight, you're going to understand what this structure really is, how we found it, and why it's forcing cosmologists to reconsider the fundamental rules of how the universe works. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why this discovery is so profound, we need to start with how astronomers thought the universe was supposed to look. There's a principle in cosmology, one of the foundational ideas of modern science. It's called the cosmological principle, and it states something simple but powerful. On sufficiently large scales, the universe should be homogeneous and isotropic. Homogeneous means it's the same everywhere. Isotropic means it looks the same in all directions. Now, this doesn't mean every cubic meter of space contains the same stuff. Obviously, it doesn't. We have stars, planets, empty space, galaxies, voids. There's tremendous variation on small scales. But if you zoom out far enough, if you average over large enough volumes of space, the universe should start to look uniform. Think of it like a sandy beach. Up close, you see individual grains. Some larger, some smaller, some light-colored, some dark. Variation everywhere. But step back and look at the whole beach from a distance. It looks uniform, the same tan color everywhere. The variations average out. The cosmological principle says the universe works the same way. Zoom out far enough, and it should look smooth and uniform. Based on observations and theoretical calculations, cosmologists determined that you need to average over scales of about 1,200,000,000 light-years. At that scale and larger, the universe should be homogeneous. No structure should exist larger than that. This makes sense given what we understand about the universe. The universe is about 13.8 billion years old. It started with the Big Bang, an incredibly hot and dense state. In the first few 100,000 years, matter was too hot to clump together. Atoms couldn't form. Everything was a soup of particles and radiation. Eventually, the universe cooled enough for atoms to form. Light could finally travel freely through space. This happened about 380,000 years after the Big Bang. After atoms formed, gravity could start pulling matter together, but gravity is slow. It takes time to build structure. The first stars formed a few 100 million years after the Big Bang. The first galaxies formed maybe 500 million to 1 billion years later. These galaxies merged and grew over billions of years, eventually forming the galaxy clusters and superclusters we see today. The key point is that there hasn't been enough time since the Big Bang for gravity to build structures larger than about 1,200,000,000 light-years. Anything larger than that would require matter from regions of space that were too far apart to have influenced each other gravitationally. Information, including gravitational influence, can't travel faster than light. So there's a limit to how large structures can grow in the time available. This limit, the theoretical maximum size of cosmic structures, is about 1,200,000,000 light-years. Structures larger than this would violate our understanding of how the universe evolved. They would suggest that somehow gravity managed to organize matter across distances larger than light could have traveled in the age of the universe. That shouldn't be possible. Now let me tell you what astronomers found. because in 2013, astronomers found something that shouldn't fit into this picture, something that violates one of the fundamental principles of modern cosmology. Let me explain the principle first. It's called the cosmological principle. It states that on sufficiently large scales, the universe should be homogeneous and isotropic. Homogeneous means it's the same everywhere. Isotropic means it looks the same in all directions. This doesn't mean every cubic meter of space contains the same stuff. Obviously, it doesn't. We have stars, planets, empty space, galaxies, voids. There's tremendous variation on small scales, but if you zoom out far enough, if you average over large enough volumes of space, the universe should start to look uniform. Think of it like this. If you look at a sandy beach up close, you see individual grains. Some are larger, some are smaller, some are light-colored, some are dark. There's variation everywhere you look. But step back. Look at the whole beach from a distance. It looks uniform, the same tan color everywhere. The variations average out. The cosmological principle says the universe works the same way. Zoom out far enough, and it should look smooth and uniform. Based on observations and theoretical calculations, cosmologists determined that you need to average over scales of about 1,200,000,000 light-years. At that scale, and larger, the universe should be homogeneous. No structure should exist larger than that. This makes sense, given what we understand about the universe. The universe is about 13.8 billion years old. It started with the Big Bang, an incredibly hot and dense state. In the first few 100,000 years, matter was too hot to clump together. Atoms couldn't form. Everything was a soup of particles and radiation. Eventually, the universe cooled enough for atoms to form. Light could finally travel freely through space. This happened about 380,000 years after the Big Bang. The cosmic microwave background radiation we detect today is light from that era, stretched to microwave wavelengths by the expansion of the universe. After atoms formed, gravity could start pulling matter together. But gravity is slow. It takes time to build structure. The first stars formed a few 100 million years after the Big Bang. The first galaxies formed maybe 500 million to 1 billion years after the Big Bang. These galaxies merged and grew over billions of years, eventually forming the galaxy clusters and superclusters we see today. The key point is that there hasn't been enough time since the Big Bang for gravity to build structures larger than about 1,200,000,000 light-years. Anything larger than that would require matter from regions of space that were too far apart to have influenced each other gravitationally. Information, including gravitational influence, can't travel faster than light. So there's a limit to how large structures can grow in the time available. This limit, called the theoretical maximum size of cosmic structures, is about 1,200,000,000 light-years. Structures larger than this would violate our understanding of how the universe evolved. They would suggest that somehow, gravity managed to organize matter across distances larger than light could have traveled in the age of the universe. That shouldn't be possible. Now let me tell you what astronomers found. In 2013, a team of researchers led by Istvan Horvath analyzed the distribution of gamma-ray bursts. Gamma-ray bursts are the most energetic explosions in the universe. They occur when massive stars collapse into black holes or when neutron stars merge. For a brief moment, a gamma-ray burst can outshine entire galaxies. They're visible across billions of light-years. Because they're so bright, astronomers can use them as markers to map the large-scale structure of the universe. Horvath and his team were studying gamma-ray bursts detected by the SWIFT satellite. They were looking at the three-dimensional positions of these bursts, trying to understand how they're distributed across space. What they found was surprising. The gamma-ray bursts weren't evenly distributed. That wasn't surprising in itself. We expect matter to be clumped on small and medium scales. Galaxies cluster together. We know that. But the scale of the clustering they found was unexpected. There was a region of space where gamma-ray bursts were significantly more common than in surrounding regions. A huge concentration of them, far more than you'd expect from random chance. They ran statistical tests. The probability that this concentration was just a random fluctuation was less than 1 in 16,000. This wasn't noise. This was a real structure. But here's the thing. When they calculated the size of this structure, the numbers didn't make sense. It was enormous. Truly enormous. It stretched across approximately 10 billion light-years. 10 billion light-years. That's not 1,200,000,000 light-years. That's not close to the theoretical maximum. That's more than 8 times larger than the theoretical maximum size for cosmic structures. This structure became known as the Hercules Corona Borealis Great Wall, named after the constellations where it appears in our sky, Hercules and Corona Borealis. It's the largest known structure in the observable universe, and it shouldn't exist. Let me put this size in perspective, because 10 billion light-years is not a number that means anything to human intuition. Light travels at about 186,000 miles per second. In 1 year, light covers about 9.46 trillion kilometers. In 10 billion years, light covers about 94.6 billion trillion kilometers. That's 94.6, followed by 21 zeros. 94 sextillion 600 quintillion trillion kilometers. The number is meaningless. It's too large to visualize or relate to anything in human experience. So let me try a different approach. Imagine you could shrink the observable universe down to the size of Earth. The observable universe is about 93 billion light-years across. Earth is about 7,900 miles in diameter. On this scale, the Hercules Corona Borealis Great Wall would stretch roughly 800 miles. That's about the distance from New York to Miami. But remember, in this analogy, the entire observable universe is the size of Earth. Every galaxy, every star, every planet, all compressed down to fit inside something the size of our planet. And this structure spans a distance equivalent to crossing a significant portion of a continent. Let me try another comparison. The Milky Way galaxy is about 100,000 light-years across. The Hercules Corona Borealis Great Wall is 100,000 times larger than that. If the Milky Way were the size of a coin, the Great Wall would stretch over half a mile. Our entire galaxy, with its hundreds of billions of stars, reduced to something you could hold between your fingers. And this structure would extend over 3,000 feet away from that coin. The Laniakea supercluster, which contains our galaxy and about 100,000 others, spans about 520 million light-years. The Great Wall is roughly 20 times larger than Laniakea. 20 Laniakeas lined up end to end. 20 structures, each containing 100,000 galaxies, each galaxy containing hundreds of billions of stars. That's the scale we're dealing with. Now here's what makes this even more remarkable. The Great Wall isn't just large, it's old. The light we're detecting from gamma-ray bursts in this structure has been traveling for about 10 billion years. That means we're seeing this structure as it existed 10 billion years ago. The universe is 13.8 billion years old. 10 billion years ago, the universe was only about 3.8 billion years old, less than a third of its current age. For this structure to exist 10 billion years ago means it must have formed even earlier, maybe 3 billion years after the Big Bang, maybe 2 billion years after the Big Bang. This creates a serious problem for cosmology. How did gravity organize matter across 10 billion light-years in only a few billion years. It shouldn't be possible. The speed of light sets a limit on how quickly gravitational influence can propagate. You can't pull on something that's so far away that light hasn't had time to travel between you. For this structure to form, matter would need to have been influenced by gravity across distances that light couldn't have crossed in the time available. Some astronomers have questioned whether the Great Wall is real. Maybe it's a statistical fluke. Maybe the apparent concentration of gamma-ray bursts is just a random clustering that looks like a structure but isn't actually connected. This is a fair question. Gamma-ray bursts are rare. We don't have millions of them to work with. The original study analyzed 14 gamma-ray bursts in this region. With small sample sizes, it's possible to see patterns that aren't really there. Maybe we're seeing faces in clouds. But follow-up studies have strengthened the case that this is real. In 2015, Horvath and colleagues published additional analysis using more gamma-ray bursts. The structure remained. The statistical significance remained strong. Other researchers have looked at the distribution of quasars in this region. Quasars are extremely bright galactic cores powered by supermassive black holes actively feeding on matter. Like gamma-ray bursts, they're visible across vast distances, and there's a concentration of quasars in the same region as the gamma-ray bursts. This suggests that there really is an overdensity of matter in this part of the sky. More galaxies, more activity, more objects clustered together across an enormous volume of space. Other large structures have been found as well. The Sloan Great Wall, discovered in 2003, spans about 1.4 billion light-years. That's larger than the theoretical maximum, but only by about 17%. It's borderline. Maybe it formed through rare fluctuations in the early universe. Maybe our theoretical calculations are slightly off. It pushes the boundaries but doesn't completely shatter them. The giant arc, discovered in 2021, stretches about 3.3 billion light-years across. This is well beyond the theoretical maximum. It's another structure that challenges our understanding. But the Hercules Corona Borealis Great Wall is in a category of its own. At 10 billion light-years, it's not just slightly over the limit, it's not borderline. It's 3 times larger than the giant arc. It's 7 or 8 times larger than the Sloan Great Wall. It's so far beyond what should be possible that it forces us to reconsider fundamental assumptions. So, what's going on? How do we explain this? There are several possibilities. First, maybe the cosmological principle is wrong. Maybe the universe isn't homogeneous on large scales. Maybe there's more structure, more variation, more clumpiness than we thought. This would be a profound shift in our understanding. The cosmological principle isn't just a nice idea. It's a cornerstone of modern cosmology. It underlies our models of how the universe formed and evolved. It's why we can use the cosmic microwave background radiation to study the early universe. If the cosmological principle is wrong, many of our cosmological models would need to be revised. But there's good evidence supporting the cosmological principle. The cosmic microwave background is remarkably uniform. Temperature variations are only about 1 part in 100,000. That uniformity suggests the early universe was indeed very smooth and homogeneous. Surveys of galaxies show that on scales larger than about 1 billion light-years, the universe does appear to become more uniform. The Great Wall might be a rare exception rather than evidence that the principle is fundamentally wrong. Second possibility is that our statistical methods are misleading us. Maybe the concentration of gamma-ray bursts isn't as significant as it appears. Maybe when you account for all the different ways you could search for structures in the data, the probability of finding something isn't 1 in 16,000. Maybe it's much higher. This is called the look elsewhere effect. If you search through data looking for patterns, you'll eventually find something that looks significant just by chance. The more places you look, the more likely you are to find a false positive. Imagine you're flipping a coin. You flip it 10 times, and you get 10 heads in a row. That's incredibly unlikely. The odds are 1 in 1,024. But if you flip a coin 10 times, over and over, hundreds of times, eventually you'll get 10 heads in a row. It's unlikely in any single sequence, but almost guaranteed if you try enough times. The same principle applies to astronomical data. If you search through the positions of gamma-ray bursts looking for clusters, you might find something that looks like a structure just because you looked in enough places. However, the researchers have addressed this. They've calculated the probability accounting for the look elsewhere effect. The significance drops, but it's still strong enough to suggest the structure is real. Third possibility is that the Great Wall isn't as large as it appears. Maybe it's a projection effect. Imagine you have a bunch of grapes scattered on a table. From above, they look randomly distributed. But if you look at them from the side, from just the right angle, some of them might line up. It might look like a straight line of grapes, but it's not a structure. It's just a coincidence of viewing angle. The grapes aren't actually connected. They're at different distances from you. They just happen to line up from your perspective. Maybe the Great Wall is similar. Maybe there are several unrelated structures at different distances that happen to line up along our line of sight. From our perspective on Earth, they look like one enormous structure, but in reality, they're separate. This is possible. Determining precise distances to gamma-ray bursts is difficult. We measure their redshift, which tells us how much the universe has expanded since the light was emitted. Greater redshift means greater distance. But measuring redshift requires identifying the host galaxy of the gamma-ray burst and then measuring the spectrum of that galaxy's light. This isn't always possible. Gamma-ray bursts fade quickly. By the time telescopes can observe the location, the burst itself is gone. Sometimes the host galaxy is too faint to detect. Sometimes there's ambiguity about which galaxy actually hosted the burst. So the distances to individual gamma-ray bursts have uncertainty. Maybe the Great Wall is really several smaller structures at slightly different distances that we're mistakenly interpreting as one continuous structure. But even if that's true, the individual structures would each be enormous. Breaking a 10 billion light-year structure into 5 separate structures still gives you 5 structures that are each 2 billion light-years across. That's still larger than the theoretical maximum. You've reduced the problem, but you haven't eliminated it. Fourth possibility is that our understanding of structure formation is incomplete. Maybe there are processes in the early universe that we don't fully understand. Maybe dark matter behaved differently than we think. Maybe there were density fluctuations larger than we expected. Cosmic inflation, the theory that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang, predicts that quantum fluctuations got stretched to cosmic scales. These fluctuations seeded the formation of structure, but inflation is still a theoretical framework. We don't know all the details of how it worked. Maybe under certain conditions, inflation could have created larger fluctuations than standard models predict. Fluctuations that could grow into structures larger than 1,200,000,000 light-years. This is speculative. We'd need new physics to make it work. But the Great Wall itself is evidence that something we don't understand is happening. Fifth possibility is that the structure isn't gravitationally bound. Maybe it's just a region of space where galaxies happen to be more common, not because gravity has organized them into a structure, but because of the initial conditions of the universe. Maybe this region of space just started out with more matter. In that case, it wouldn't violate our understanding of structure formation because it wouldn't be a structure that formed through gravitational collapse. It would just be an initial condition. a large-scale density fluctuation from the very early universe that never needed to collapse gravitationally. But this just pushes the question back one step. Why would there be such a large density fluctuation? What caused it? And if density fluctuations this large are possible, why don't we see more of them? As of now, we don't have a definitive answer. The Hercules Corona Borealis Great Wall remains unexplained. It sits uncomfortably at the edge of our understanding, challenging our theories but not completely breaking them. It's a reminder that the universe is under no obligation to make sense to us. Our models and theories are approximations, attempts to describe reality based on the limited information we can gather. Sometimes reality surprises us. Sometimes we find things that don't fit neatly into our frameworks. And that's when science gets interesting, because anomalies drive progress. When observations don't match predictions, we have to figure out why. Either the observations are wrong, or the predictions are wrong. Either way, we learn something. We refine our instruments. We develop better theories. We expand our understanding. The Great Wall might turn out to be less significant than it appears. Maybe future observations will show it's not as large as we thought. Maybe it will break apart into smaller structures, or maybe it will remain a genuine anomaly that forces us to revise our cosmological models. Maybe the universe is lumpier than we thought, on large scales. Maybe the cosmological principle applies on some scales, but not all. Maybe there are processes in the early universe we haven't discovered yet. Either way, it's remarkable that we can even ask these questions. We're standing on a small planet, orbiting an ordinary star in one galaxy among trillions. And we've mapped structures 10 billion light-years across. We've measured the distribution of matter across a significant fraction of the observable universe. We've detected explosions so distant that their light has been traveling for 10 billion years. We've used mathematics and physics to calculate what structures should and shouldn't be possible, and we've found something that challenges those calculations. That's extraordinary. Let me put the Great Wall in one more context. The observable universe is roughly 93 billion light-years across. That's the distance light has been able to travel since the Big Bang, accounting for the expansion of the universe. The Hercules Corona Borealis Great Wall spans about 10 billion light-years. That's more than 10% of the entire observable universe. Imagine you could see the whole observable universe at once, all 93 billion light-years of it. This structure would stretch across more than a tenth of everything you could see. It's not just large by astronomical standards. It's large even by cosmic standards. Even compared to the entire observable universe, it's massive. Now think about what this structure contains. It's not empty space. It's a concentration of matter. Galaxies, galaxy clusters, gas, dark matter. Estimating the exact number of galaxies is difficult because we can't observe the Great Wall in detail. It's too distant. We're detecting its presence through the distribution of gamma-ray bursts and quasars, not by directly seeing all the galaxies, but we can make rough estimates. The universe contains about 2 trillion galaxies in total. They're not evenly distributed. They're concentrated in filaments and clusters with voids in between. If the Great Wall is a dense region, it might contain a higher than average concentration of galaxies. Maybe it contains hundreds of billions of galaxies, maybe trillions. Each galaxy containing hundreds of billions of stars. The total number of stars in the Great Wall could be measured in sextillions. That's a 1, followed by 21 zeros. Each star potentially hosting planets. Each planet potentially hosting moons, asteroids, comets. The number of worlds in this structure is beyond comprehension, and somewhere in that vast collection of galaxies, there might be other civilizations. Other beings looking up at their night sky, wondering about the cosmos. Maybe some of them are advanced enough to have mapped their region of space. Maybe they've discovered that they're part of an enormous structure. Maybe they're asking the same questions we are. Why does this structure exist? How did it form? What does it mean? We have no way to know. The distances are too great. The light travel time is too long. Even if there are civilizations in the Great Wall trying to communicate, their signals would take billions of years to reach us. By the time we received a message, the civilization that sent it might be long gone. And if we sent a message back, billions more years would pass before it arrived. Communication across these distances isn't practical. It's barely even meaningful. But the structure exists regardless of whether anyone is observing it or thinking about it. 10 billion light-years of concentrated matter, spanning a significant fraction of the observable universe. A structure so large that it challenges our understanding of cosmic evolution. Let's think about time for a moment. We're seeing the Great Wall as it existed 10 billion years ago. The light we're detecting left those galaxies when the universe was less than 4 billion years old. What does the Great Wall look like now, today, in the present moment? We can't know. We can't see it in its current state. Light takes time to travel. By the time light from the present-day Great Wall reaches Earth, 10 billion more years will have passed. The Sun will have long since died. Earth will have been destroyed. Humanity will either have moved to other star systems or gone extinct. Our entire civilization will be ancient history, and only then will the light from the Great Wall as it exists right now reach the empty space where Earth once orbited. This is one of the strange consequences of the finite speed of light. We can only see the past. The farther we look in space, the farther we look back in time. The Great Wall we observe existed when the universe was young. Stars were forming at a much higher rate back then. Galaxies were colliding and merging more frequently. The universe was denser, hotter, more active. In the 10 billion years since, the Great Wall has continued to evolve. Stars have been born and died. Galaxies have moved, merged, changed. The structure has aged along with the rest of the universe, but we'll never see what it looks like now. We're permanently locked into observing its past. This is true for everything in the universe. When you look at the moon, you're seeing it as it was 1.3 seconds ago. That's how long light takes to travel from the moon to Earth. The Sun appears as it was 8 minutes and 20 seconds ago. The nearest star, 4.24 years ago. The Andromeda Galaxy, 2.5 million years ago. Distant quasars, billions of years ago. Everything you see in the night sky is a fossil record of cosmic history. You're looking at the universe not as it is, but as it was. The Great Wall represents one of the oldest fossils we can observe. A snapshot of cosmic structure from when the universe was in its youth, and it tells us something profound. Even 10 billion years ago, even when the universe was less than a third of its current age, enormous structures already existed. Matter had already organized itself on scales we can barely comprehend. The universe was already complex, already filled with intricate patterns of matter and energy. This raises questions about the even earlier universe. What happened in the first billion years? How quickly did structure form? What were the conditions that allowed such large structures to emerge? These are active areas of research. Telescopes, like the James Webb Space Telescope, are designed specifically to look at the early universe, to see the first galaxies, the first stars, the first large structures. We're learning that the early universe was more complex than we expected. Galaxies formed earlier than we thought. Massive galaxies existed when the universe was only a few 100 million years old. The first stars ignited sooner than our models predicted. Structure formation happened faster than we calculated. The Great Wall fits into this picture of a universe that organized itself quickly. Maybe 10 billion years ago, structures as large as the Great Wall were rare but not impossible. Maybe our theories are mostly right, but missing some details. Maybe there's new physics waiting to be discovered. Or maybe we're just seeing the universe during a special time. Maybe structures this large were more common in the past. Maybe the expansion of the universe has since spread things out, making such large structures less likely to form now. In the future, as the universe continues to expand, galaxies will drift farther apart. Galaxy clusters will become more isolated. Structure formation will slow down. Eventually, the expansion will accelerate to the point where even gravity can't pull things together anymore. In the far future, trillions of years from now, the universe will be cold, dark, and empty. Galaxies will have exhausted their gas supplies. Star formation will have stopped. Existing stars will have burned out. Black holes will have evaporated. The universe will be mostly empty space, with occasional radiation and particles drifting through the void. Any structures that exist will be relics from an earlier, more active era. The Great Wall, if it survives in any form, will be a dark, lifeless collection of dead galaxies. But that's far in the future. Right now, the Great Wall exists as a massive, active structure. Stars are forming, living, dying. Galaxies are orbiting within clusters, slowly drifting under the influence of dark matter. Black holes are consuming matter and releasing energy. The structure is alive in a cosmic sense. It's evolving, changing, participating in the ongoing story of the universe, and we get to observe it. We get to study it. We get to puzzle over its existence and try to understand what it means. That's the privilege of living in this era. We have the technology to see across billions of light years. We have the knowledge to interpret what we see. We have the mathematical tools to model cosmic structure formation. We can stand on our small planet and contemplate structures that span 10 billion light years. Our ancestors looked up at the night sky and saw dots of light. They invented stories to explain the patterns. Constellations, gods, myths. They had no way to know that those points of light were distant suns. They couldn't conceive of galaxies or cosmic structures. The universe they imagined was tiny compared to reality. We know better now. We know the stars are suns. We know galaxies are collections of billions of stars. We know the universe is vast beyond imagination. And we know that even within that vastness, there are structures so large they challenge our understanding. The Hercules Corona Borealis Great Wall is the largest of these structures, 10 billion light-years across. A concentration of galaxies, gas, and dark matter spanning more than 10% of the observable universe. It's a reminder that the cosmos operates on scales we're only beginning to grasp. Every time we think we understand the limits, we find something that pushes beyond them. Every time we think we've mapped the universe, we discover something new. The Great Wall might not be the largest structure that exists. It's just the largest we've found so far. There might be others farther away, outside our current observational reach. There might be structures we can't detect because they don't emit gamma-ray bursts or contain bright quasars. The universe might be full of enormous structures we haven't noticed yet, or the Great Wall might genuinely be exceptional. A rare giant, one of the largest structures that could possibly form given the age and conditions of our universe. We don't know yet. We need more data, more observations, better telescopes, more sophisticated models. Over the next decades, as we build more powerful instruments and gather more information, we'll refine our understanding. We'll learn whether the Great Wall is unique or common. We'll figure out how it formed. We'll understand whether it requires new physics or whether it fits within our existing theories. This is how science progresses. Observation, hypothesis, testing, refinement. Each generation builds on the work of the previous generation. Each discovery raises new questions. Each answer reveals how much we still don't know. The Hercules Corona Borealis Great Wall is one of those discoveries that expands our perspective. It forces us to think bigger, to question our assumptions, to recognize that the universe might not play by the rules we expect. It's humbling and exciting at the same time. Humbling because it reminds us how much we don't know. Exciting because it points toward new discoveries waiting to be made. Somewhere out there, in the vastness of space, this enormous structure exists. Right now, in the present moment that we can never observe, it's continuing to evolve. Stars are being born in its galaxies. Planets are forming around those stars. Black holes are merging. Gas is flowing, cooling, heating, cycling through generations of star formation. The structure is dynamic, alive with activity. And 10 billion years from now, if there's anyone around to observe it, they'll see it as it is today. They'll see our era, our moment in cosmic history. They'll study the galaxies as they existed at this time. They'll analyze the distribution of matter. They'll try to understand how this structure formed and evolved, and maybe they'll be puzzled, just as we are. Maybe they'll find that the Great Wall as it exists in our era is just as mysterious to them as the Great Wall of 10 billion years ago is to us. Time is strange at cosmic scales. Past, present, and future blur together. What we see is the past. What exists now is invisible to us. What will be in the future is unknowable. All we have is this moment, this observation, this snapshot of a structure from an ancient era, but that snapshot is enough. It tells us something profound about the universe. It tells us that structure formation can operate on scales larger than we predicted. It tells us that even in the early universe, matter was organizing itself in ways we're still trying to understand. It tells us that the cosmos is full of surprises. And maybe that's the most important lesson. The universe doesn't care about our theories. It doesn't care about our predictions or our expectations. It simply exists, following the laws of physics, evolving according to the initial conditions set at the Big Bang and the fundamental forces that govern matter and energy. Sometimes, that evolution produces things we expect. Sometimes it produces things that surprise us. The Great Wall is one of those surprises. A structure so large it shouldn't exist, but does. A concentration of matter spanning 10 billion light-years. The largest known object in the observable universe. And it's out there right now, existing regardless of whether we understand it. That's the beauty of science. The universe is what it is. Our job is to observe, to measure, to calculate, to try to understand. Sometimes we succeed. Sometimes we're puzzled. But either way, we keep looking. We keep learning. We keep pushing the boundaries of what we know. The Hercules Corona Borealis Great Wall is one of those boundaries. A structure at the edge of our understanding. 10 billion light-years of matter, organized in ways that challenge our theories. It's a reminder that we live in a universe far stranger and more magnificent than we often realize. A universe where structures can span distances that light takes 10 billion years to cross. A universe where matter organizes itself on scales that dwarf galaxies. A universe that continues to surprise us every time we look deeper. So the next time you look up at the night sky, remember what's out there. Remember that beyond the stars you can see, beyond the Milky Way, beyond the local group and the superclusters, there are structures so vast they seem impossible. Remember that the universe is larger and more complex than human intuition can grasp. Remember that we're part of something extraordinary, a cosmos that built stars and galaxies, and eventually us. A cosmos that gave rise to conscious beings who can look back and try to understand where they came from. We're made of atoms, forged in stars. We're standing on a planet orbiting one of those stars. We're living in a galaxy that's part of a supercluster. And that supercluster is tiny compared to the largest structures in the universe. We're small, unimaginably small compared to structures like the Hercules Corona Borealis Great Wall. But we're also remarkable. We can think about these things, we can measure them, we can study them, we can try to understand them. That ability, that capacity for understanding, is perhaps the most extraordinary thing in the universe. Not the size of structures, not the number of stars, not the vast distances or the enormous scales, but the fact that within all that vastness there emerged beings who can comprehend it, who can look at a 10 billion light-year structure and ask how it formed, who can question whether it should exist, who can use mathematics and physics to explore the limits of what's possible. That's what makes us special. Not our size, but our understanding. Not our power, but our curiosity. Not our importance in the cosmic scheme, but our ability to appreciate that cosmic scheme. The Hercules Corona Borealis Great Wall is the largest known structure in the universe. It spans 10 billion light-years. It contains unimaginable numbers of galaxies and stars. It challenges our theories of how cosmic structure forms, and it reminds us that the universe is far more complex and surprising than we often give it credit for. Thank you for joining me on this journey across cosmic scales. If you found this exploration valuable, a like or subscribe helps this channel continue exploring the deepest questions about our universe. The cosmos is vast. We are small. But together, we can understand things larger than ourselves, and that understanding is worth celebrating. But before we finish tonight, I want to take you deeper into what this structure really means. Because understanding the Great Wall isn't just about knowing its size, it's about understanding what it tells us about the universe itself, about the forces that shape cosmic structure, about the limits of our knowledge, and about the questions that still remain unanswered. Let's talk about how astronomers actually mapped this structure, because finding something 10 billion light-years across isn't like spotting a building or even a planet. You can't just point a telescope at it and take a picture. The Great Wall doesn't emit light as a single object. It's not glowing. It's not visible in the way a galaxy or a star is visible. Instead, astronomers had to piece together its existence from clues, from patterns in data, from the distribution of distant, violent events scattered across billions of light-years. Gamma-ray bursts are the key. These are the brightest explosions in the universe. They happen when massive stars much larger than our Sun, reach the end of their lives. A massive star burns through its nuclear fuel over millions of years. It fuses hydrogen into helium, helium into carbon, carbon into heavier elements, all the way up to iron. Each fusion reaction releases energy. This energy creates pressure that pushes outward. The pressure balances the gravitational pull inward. The star remains stable, but iron is different. Fusing iron doesn't release energy. It consumes energy. So when a massive star's core turns to iron, fusion stops. The pressure disappears. Nothing holds the star up against its own gravity anymore. The core collapses. In less than a second, a core the size of Earth collapses to a sphere maybe 12 miles across, a neutron star. Or if the star is massive enough, it collapses past even that point. It becomes a black hole. The collapse happens so fast that the outer layers of the star haven't had time to react. They're still falling inward when the core suddenly stops collapsing. The infalling matter crashes into the newly formed neutron star, or black hole. It bounces. A shockwave races outward through the star. The star explodes. A supernova. For a brief time, a single dying star can outshine an entire galaxy. But some supernovas are different. Some produce gamma-ray bursts. When the core collapses into a black hole, it can create jets. beams of matter and energy shooting out along the rotation axis of the collapsing star. These jets move at nearly the speed of light. They punch through the outer layers of the star and blast into space. If one of these jets happens to be pointed at Earth, we see a gamma ray burst, a flash of the most energetic radiation in the electromagnetic spectrum, gamma rays. The burst might last a few seconds, maybe a few minutes, then it fades. But for those few seconds, it's visible across billions of light years. Telescopes in space detect these bursts. Satellites like Swift and Fermi monitor the entire sky, watching for sudden flashes of gamma rays. When they detect a burst, they quickly determine its location. Within seconds, they alert ground-based telescopes. The ground telescopes swing into position and start observing the afterglow. The afterglow is the fading light from the explosion. It's visible in X-rays, visible light, radio waves. It can last for hours or days or weeks, gradually fading as the energy dissipates. By studying the afterglow, astronomers can identify the host galaxy, the galaxy where the star exploded. They measure the spectrum of that galaxy's light. The spectrum shows dark lines where specific elements have absorbed light. Those lines are shifted toward the red end of the spectrum, redshift. The expansion of the universe stretches light as it travels. The more the universe has expanded during the light's journey, the more the light is stretched. Greater redshift means greater distance. By measuring the redshift, astronomers can calculate how far away the galaxy is, and therefore, how far away the gamma-ray burst was. Over years and decades, astronomers build up a catalogue of gamma-ray bursts, hundreds of them, each one with a measured position on the sky and a calculated distance. Now you can map them, plot them in three-dimensional space. Each burst becomes a point in a vast three-dimensional map of the universe. And when you look at that map, you start to see patterns, clusters, voids, filaments, the cosmic web. This is what Horvath and his team were doing. They were looking at the three-dimensional positions of gamma-ray bursts detected by the Swift satellite, and they noticed something odd. In a particular region of sky, toward the constellations Hercules and Corona Borealis, there were more gamma-ray bursts than expected. Not just a few more, significantly more. They ran statistical tests. Is this clustering real, or just a random fluctuation? If gamma-ray bursts were distributed randomly across space, what's the probability you'd see a clustering this strong just by chance? The answer came back, less than 1 in 16,000. This wasn't noise. This was a real concentration of gamma-ray bursts, which meant a real concentration of massive stars dying, which meant a real concentration of galaxies, which meant a real structure. They calculated its size. 10 billion light-years, the largest structure ever found. But here's the challenge with a discovery like this. You're not seeing the structure directly. You're inferring it from the distribution of gamma-ray bursts. You're assuming that where there are more gamma-ray bursts, there are more galaxies, and where there are more galaxies, there's more mass. That assumption is reasonable. Gamma-ray bursts come from massive stars. Massive stars form in galaxies. More galaxies means more massive stars, means more gamma-ray bursts. The logic holds. But it's indirect. You're not photographing the Great Wall. You're detecting events happening within it and using those events to trace out its shape. It's like trying to map a city at night by looking at where lightning strikes. Lightning is more common in some areas than others. By tracking lightning strikes over time, you could eventually build a map of where storms tend to form. You'd see patterns, but you wouldn't be seeing the city directly. You'd be inferring its presence from the weather patterns it creates. The Great Wall is similar. We see the gamma-ray bursts. We infer the structure. To strengthen the case, Astronomers have looked at other tracers, quasars, for example. Quasars are among the brightest objects in the universe. They're the active cores of galaxies. At the center of most large galaxies sits a supermassive black hole, millions or billions of times the mass of the Sun. Usually, these black holes are quiet. They're not actively feeding on matter. They just sit there, exerting gravitational influence on the surrounding stars. But sometimes, gas falls toward the black hole, maybe from a star that wandered too close and got torn apart, maybe from a collision with another galaxy that sent gas streaming into the center. The gas doesn't fall straight in. It has angular momentum. It spirals inward, forming a disk around the black hole, an accretion disk. As the gas spirals inward, it heats up. Friction between particles in the disk converts gravitational potential energy into heat. The disk becomes incredibly hot, millions of degrees, hot enough to emit X-rays and ultraviolet light. The disk can outshine all the stars in the galaxy combined. From Earth, we see this as a quasar, a brilliant point of light. So bright that the surrounding galaxy is often invisible, washed out by the glare from the central black hole. Quasars, like gamma-ray bursts, are visible across vast distances. We can detect quasars billions of light-years away. And like gamma-ray bursts, we can measure their redshifts and map their positions in three-dimensional space. When astronomers looked at the distribution of quasars in the same region as the gamma-ray bursts, they found the same thing: a concentration. More quasars than expected. This strengthens the case that the Great Wall is real. Two independent tracers, gamma-ray bursts and quasars, both showing enhanced density in the same region of space. It's unlikely that both are random fluctuations. More likely, there's genuinely more matter there. More galaxies, more activity, more structure. But even with this evidence, some astronomers remain skeptical. The sample sizes are small. We're talking about dozens of gamma-ray bursts, not thousands. Hundreds of quasars, not millions. With small numbers, statistical flukes are possible. Maybe we're seeing a pattern that isn't really there. Maybe the structure will disappear when we gather more data. This is a healthy skepticism. Science requires evidence. Extraordinary claims require extraordinary evidence. A structure 10 billion light-years across, violating theoretical predictions, is an extraordinary claim. It demands rigorous scrutiny. Over the coming years, as more gamma-ray bursts are detected and more quasars are catalogued, we'll refine our understanding. If the Great Wall is real, the evidence will strengthen. The concentration will remain or become even more significant. If it's a statistical fluke, it will weaken. The apparent clustering will fade as more data is added. Time will tell. But for now, based on the available evidence, most astronomers accept that there's something there, a large-scale structure, possibly the largest in the universe. Now let's think about what it would be like to actually be inside the Great Wall. Imagine you're an astronomer on a planet, orbiting a star in a galaxy within this structure. What would you see? First, understand that even though the structure is enormous, it's not dense. Space is mostly empty, even within structures like this. The Great Wall isn't a solid object. It's not packed with galaxies shoulder to shoulder. It's a region where galaxies are somewhat more common than in surrounding space. Think of it like a crowd. In an empty field, people are spread out randomly. In a city, people are more concentrated, but there's still space between them. The Great Wall is like that. A city of galaxies in an otherwise empty field of space. From your planet inside one of those galaxies, you'd look up at the night sky. You'd see stars, just like we do. Stars from your own galaxy. You might see other galaxies if your instruments are sensitive enough. Nearby galaxies in your cluster. more distant galaxies scattered across the sky. Would you notice that you're in a large-scale structure? Probably not directly. The galaxies around you would look similar to galaxies elsewhere in the universe. There's no visible boundary to the Great Wall, no edge you could point to. It's a statistical excess, a region where, if you counted galaxies carefully, you'd find more than the cosmic average. But you'd need to survey a huge volume of space to notice the difference. You'd need to map millions of galaxies and analyze their distribution. Only then would the pattern emerge. You'd see that galaxies in your region are slightly more clustered, that the density is a bit higher than it should be, that you're part of a large-scale structure. This is similar to our own situation. We live in the Milky Way, which is part of the local group, which is part of the Virgo supercluster, which is part of the even larger Laniakea supercluster. From Earth, we don't see a sign in the sky saying, "You are here in Laniakea." We discovered our place in these structures by painstakingly mapping the positions and motions of galaxies, by measuring redshifts and distances, by building three-dimensional maps and looking for patterns. It took decades of work by thousands of astronomers. The same would be true for someone inside the Great Wall. They'd need sophisticated instruments, careful observations, and statistical analysis to realize they're part of an enormous structure. Now let's think about motion. Galaxies in the Great Wall aren't stationary. They're moving under the influence of gravity. Each galaxy feels the gravitational pull of every other galaxy. The structure as a whole is evolving. Galaxies are orbiting within clusters. Clusters are slowly drifting through the larger structure. Everything is in motion, but it's slow motion by human standards. Galaxies move at hundreds of miles per second. That sounds fast. It is fast. But over the vast distances involved, it takes millions or billions of years for significant changes to occur. A galaxy moving at 300 miles per second will cross 1 million light-years in about 2 billion years. The Great Wall is 10 billion light-years across. Crossing it would take trillions of years. So the structure is essentially frozen from a human perspective. It exists now much as it existed 10 billion years ago when the light we're seeing left it. It will exist in much the same form billions of years from now. The overall shape might change slightly. Some clusters might merge. Some galaxies might drift apart, but the large-scale structure will persist, unless something disrupts it. And here's an interesting question. What could disrupt a structure this large? In our region of space, we know that galaxies collide. The Milky Way and Andromeda are on a collision course. They'll merge in about 4 billion years. This will disrupt both galaxies. Stars will be scattered. The spiral structures will be destroyed. A new elliptical galaxy will form. But this only affects the two galaxies involved. It doesn't affect the larger structures they're part of. The local group will still exist, just with one large galaxy instead of two medium ones. Similarly, galaxy clusters can merge. When two clusters collide, they create spectacular fireworks. Gas between the galaxies heats to millions of degrees. It glows in X-rays. The collision can trigger bursts of star formation. But again, this only affects the clusters involved. On the scale of the Great Wall, cluster mergers are minor events. They don't destroy the overall structure. What about the expansion of the universe? The universe is expanding. Space itself is stretching. Galaxies are moving apart not because they're traveling through space, but because the space between them is increasing. On small scales, gravity dominates. The Milky Way and Andromeda are gravitationally bound to each other. The expansion of the universe is too weak to overcome their mutual attraction. They're falling toward each other despite the expansion. Similarly, galaxy clusters are gravitationally bound. The expansion doesn't pull them apart. But on larger scales, Structures that aren't strongly bound can be stretched by expansion. The Great Wall is so large that different parts of it are receding from each other due to cosmic expansion. Over billions of years, this will cause the structure to stretch and eventually fade. Galaxies at opposite ends of the Great Wall are moving apart. The distance between them is increasing. Eventually, they'll lose any connection. They'll be part of different, isolated structures. The Great Wall as a coherent entity will dissolve. This won't happen quickly. It will take many billions of years, possibly tens of billions of years. But eventually, cosmic expansion will win. Even structures as large as the Great Wall can't resist the expansion forever. In the far future, the universe will be very different. The expansion is accelerating. Something called dark energy is driving galaxies apart faster and faster. We don't know what dark energy is. It's one of the biggest mysteries in physics. But we know it exists because we can measure its effects. Distant galaxies are receding faster than they should be based on the expansion rate we measure nearby. Something is accelerating the expansion. We call that something dark energy. In the far future, dark energy will dominate. Galaxy clusters will become isolated islands in an ever-expanding ocean of space. Eventually, galaxies outside our local gravitational neighborhood will recede so fast that their light can't reach us anymore. The observable universe will shrink, not in physical size, but in how much of the universe we can see. Light from distant galaxies will be stretched to infinite wavelengths. It will effectively disappear. Future astronomers, if they exist, will look up and see only their local cluster. Everything else will be beyond their observational horizon. They won't be able to see the cosmic microwave background. They won't be able to study the early universe. They won't know about the Big Bang unless their civilization preserves the knowledge we're gathering now. This is one reason why astronomy is so important today. We live in a special time, a time when the universe is old enough to have developed complex structures and intelligent life, but young enough that we can still see most of the universe. We can study the cosmic microwave background. We can observe distant galaxies. We can map structures like the Great Wall. Future civilizations won't have this opportunity. The evidence will have receded beyond the horizon. So, in a sense, we're responsible for documenting the universe while we still can, for future generations who won't be able to see what we see. This gives our astronomical observations a kind of historical importance. We're not just satisfying curiosity, we're preserving knowledge that will eventually become inaccessible. The Great Wall is part of that knowledge. A structure so large it spans 10% of the observable universe. A concentration of matter that challenges our theories. A reminder that the cosmos is more complex than our models suggest. Let's think about what the Great Wall tells us about the universe on the largest scales. One of the fundamental questions in cosmology is, what does the universe look like overall? If you could step back and see the whole universe at once, what would you see? We can't actually do this, of course. We're stuck inside the universe. We can only observe the part that's visible from our location, but we can try to understand the overall structure by studying what we can see. The cosmological principle says the universe should be homogeneous and isotropic on large scales. Everywhere should look roughly the same. Every direction should look roughly the same. This principle is supported by observations. The cosmic microwave background looks the same in all directions to about 1 part in 100,000. That's remarkably uniform. It suggests the early universe was very smooth and homogeneous. Surveys of galaxies also support the principle. When you average over large enough volumes, the density of galaxies becomes uniform. The number of galaxies per cubic gigaparsec is roughly constant across the observable universe. A gigaparsec is about 3.26 billion light-years, so we're talking about truly enormous volumes. And within those volumes, the universe does appear homogeneous, but the Great Wall seems to violate this. At 10 billion light-years, it's larger than the scale at which the universe should be smooth. It's a significant lump in what should be a uniform distribution. This creates tension between observation and theory. Either the observation is wrong, or the theory needs adjustment. Let's consider the possibility that the observation is wrong. Maybe the Great Wall isn't as large as it appears. Maybe it's a projection effect. Several smaller structures lined up along our line of sight. This is possible, but follow-up studies have tried to account for this. They've looked at the three-dimensional distribution carefully. They've checked for possible projection effects. The structure seems to hold up. It appears to be a genuine concentration of matter in a connected region of space, not a chance alignment. Alternatively, maybe the statistical significance is overstated. Maybe the clustering isn't as unlikely as it appears. This is harder to assess. Statistics can be tricky, especially with small sample sizes. Different statistical tests can give different results, but multiple independent analyses have found similar conclusions. The clustering is significant. It's unlikely to be a random fluctuation. So if the observation is probably correct, maybe the theory needs adjustment. Maybe the cosmological principle is an approximation that works on most scales but breaks down on the very largest scales. Maybe the universe isn't perfectly homogeneous, even when averaged over 1 billion light-years or more. This wouldn't completely overturn cosmology. The cosmic microwave background would still show the early universe was very uniform. But it would suggest that structure formation proceeded differently than we thought. Maybe there were larger density fluctuations in the early universe than our models predict. Maybe dark matter clumped in unexpected ways. Maybe there's some physics we don't understand yet. This is actually exciting from a scientific perspective. Anomalies drive progress. When observations don't match predictions, it means we're missing something. Either our observations are flawed or our theories are incomplete. Either way, investigating the discrepancy leads to new understanding. The Great Wall might be pointing us toward new physics. Maybe it's telling us something about dark matter. Dark matter is the invisible stuff that makes up about 85% of all matter in the universe. We can't see it directly because it doesn't emit, absorb, or reflect light. We know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by only the visible matter. There must be additional mass we can't see. Clusters of galaxies move in ways that require more mass than we can account for with visible matter. Gravitational lensing, the bending of light by massive objects, shows that galaxy clusters contain far more mass than their visible stars and gas. All of this points to dark matter, an invisible component that interacts through gravity but not through electromagnetism. The leading candidate is some kind of exotic particle, not protons, neutrons, or electrons, something else entirely. Particles that were created in the Big Bang but interact very weakly with ordinary matter. They pass through normal matter without colliding. They're all around us right now, passing through Earth, through your body, without you ever noticing. We've been trying to detect these particles directly for decades. Experiments deep underground, shielded from cosmic rays, looking for the rare occasion when a dark matter particle might collide with an atomic nucleus. So far, we haven't detected them directly, but we see their gravitational effects everywhere. Dark matter is essential for galaxy formation. Without it, galaxies wouldn't have formed. The universe would be very different. In the early universe, dark matter started clumping together first. It formed gravitational wells. Normal matter, hydrogen and helium gas, fell into these wells. The gas collected in the centers of the dark matter halos. It cooled and condensed. Eventually, it formed stars. The stars grouped into galaxies. The galaxies inherited the distribution of dark matter. Where dark matter was denser, galaxies formed more readily. Where dark matter was sparse, fewer galaxies formed. So, the large-scale structure of the universe, the cosmic web, is shaped by dark matter. The Great Wall, if it's real, is fundamentally a concentration of dark matter. The galaxies we see are just the visible markers of where dark matter has concentrated. Maybe something about dark matter's properties allowed such a large structure to form. Maybe dark matter isn't as uniform as we thought. Maybe it had larger fluctuations in density in the early universe. Maybe it clumps more efficiently than our models predict. These are speculative ideas. We don't have evidence for them yet, but the Great Wall might be a clue, a hint that our understanding of dark matter is incomplete. Another possibility involves cosmic inflation. Inflation is the theory that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. In an incredibly short time, much less than a second, the universe expanded by a factor of at least 10 to the 26. That's a 1 followed by 26 zeros. Space itself stretched faster than the speed of light. This is allowed by relativity. Nothing can travel through space faster than light, but space itself can expand at any rate. Inflation solves several problems in cosmology. It explains why the universe is so uniform on large scales. Different regions of space that seem too far apart to have ever been in contact were actually close together before inflation. They had time to reach thermal equilibrium. Then inflation stretched them apart. It explains why the universe is so flat geometrically. Inflation stretched out any curvature that might have existed. Like inflating a balloon, smooths out wrinkles on its surface. It explains why we don't see magnetic monopoles and other exotic relics that should have been created in the Big Bang. Inflation diluted them to undetectable levels. And crucially for our story, inflation explains the origin of structure. Quantum fluctuations in the inflation field got stretched to cosmic scales. These fluctuations became the seeds of galaxy clusters and superclusters, the tiny variations in density we see in the cosmic microwave background. Those variations are the imprints of quantum fluctuations from the inflation era. Over billions of years, gravity amplified these tiny fluctuations. Denser regions attracted more matter. They became galaxy clusters. Less dense regions lost matter to their denser neighbors. They became voids. The cosmic web emerged from these primordial density fluctuations. But here's the thing. Inflation predicts a certain spectrum of fluctuations, a particular distribution of sizes and amplitudes. Most fluctuations should be small. Larger fluctuations should be rarer. The largest fluctuations should produce structures no larger than about 1 billion light-years. The Great Wall is 10 billion light-years. That's not predicted by standard inflation models, so maybe standard inflation is wrong. Maybe there are variations of inflation that can produce larger fluctuations. Maybe under certain conditions, quantum fluctuations during inflation can be larger than we thought. This is an active area of research. Cosmologists are exploring different inflation models, trying to find one that explains all the observations, including, potentially, the Great Wall. Alternatively, maybe the Great Wall formed through a different mechanism entirely. Maybe it's not a gravitationally bound structure. Maybe it's a fossil from the early universe, a region that started out with more matter and has simply remained denser ever since. In this scenario, it wouldn't have formed through gravitational collapse. It would just be an initial condition, a leftover from whatever process created the universe's initial density distribution. This pushes the question back to the origin of the universe itself. Why would there be such large variations in initial density? We don't know. But it's possible. The universe might be more complex in its initial conditions than our theories assume. All of these possibilities remain open. The Great Wall is a mystery, an observation that doesn't fit neatly into our current understanding. And that's okay. Science progresses by confronting mysteries, by finding observations that challenge our theories, by using those challenges to refine and improve our understanding. The Great Wall is doing that for cosmology. It's forcing cosmologists to think carefully about their assumptions, to test their models more rigorously, to consider alternative explanations. This process might lead to new discoveries. Maybe we'll find new physics. Maybe we'll refine our understanding of dark matter or inflation. Maybe we'll discover that the universe has properties we never suspected, or maybe we'll find a simpler explanation. Maybe the Great Wall will turn out to be less significant than it appears. Maybe future observations will show it's not as large or not as coherent as we thought. Science is an ongoing process. Our understanding evolves as we gather more data. What seems mysterious today might be well understood tomorrow. What seems certain today might be overturned by new observations tomorrow. That's the nature of the enterprise. We build models based on the best available evidence. We test those models against new observations. When the models fail, we revise them. The Great Wall is part of this process. It's a data point that doesn't fit current models. It's a challenge to our understanding, and it's an opportunity to learn something new. Now let me bring this back to a human scale. Because all of this, the 10 billion light-years, the dark matter, the inflation theory, the statistical analyses, can feel very abstract and distant. What does it mean for us? We're here on Earth, a small planet orbiting an ordinary star. The Great Wall is so far away that its light has been traveling since long before Earth existed. It seems impossibly remote, irrelevant to our daily lives. In one sense, that's true. The Great Wall doesn't affect you. It doesn't influence the weather. It doesn't determine the course of human history. It's too far away to matter in any practical sense. But in another sense, it matters profoundly, because the Great Wall is part of the universe that created us. The same processes that form the Great Wall also form the Milky Way. The same dark matter that concentrates in the Great Wall also shaped our galaxy. The same inflation that produced density fluctuations on 10 billion light-year scales also produced fluctuations on smaller scales. Those smaller fluctuations became galaxy clusters. Our galaxy is in one of those clusters. The same physics operates everywhere. The same fundamental forces, the same particles, the same laws of nature. Understanding the Great Wall is part of understanding how the universe works. And understanding how the universe works is part of understanding where we came from. We're made of atoms. Those atoms were forged in stars. Those stars formed in galaxies. Those galaxies formed from density fluctuations in the early universe. Those density fluctuations were created during cosmic inflation. Inflation was part of the Big Bang. The Big Bang created space, time, matter, energy, everything that exists, including us. So when we study the Great Wall, we're studying our own origin story. We're tracing the chain of cause and effect that led from the Big Bang to this moment. To you, reading this script or listening to these words, that's not abstract, that's profound. It means we're connected to the largest structures in the universe, not just philosophically, physically. The same events that created the Great Wall created the matter in your body. You and the Great Wall are made of the same stuff, shaped by the same cosmic processes. You're small, unimaginably small compared to a structure 10 billion light-years across. But you're also part of the same story. The same universe that built the Great Wall also built you. And you have something the Great Wall doesn't have: consciousness. The ability to think, to wonder, to ask questions. The Great Wall exists, but it doesn't know it exists. You exist, and you can know about the Great Wall. You can comprehend distances that dwarf galaxies. You can understand physics that operates on scales from the quantum to the cosmic. You can trace the history of the universe, from the Big Bang to the present moment. That's extraordinary. That's what makes us special in the universe. Not our size, not our power, not our longevity, but our ability to understand, our capacity for knowledge, our curiosity about how things work and where we came from. The Great Wall is the largest structure we've ever found, but finding it required human ingenuity, building satellites to detect gamma-ray bursts, developing mathematical techniques to analyze three-dimensional distributions, creating theories of cosmic structure formation, testing those theories against observations. All of this is a testament to what we can accomplish as a species. We're small, but we're mighty in our ability to understand the cosmos. So when you think about the Hercules Corona Borealis Great Wall, don't just think about its size, think about what it represents: a challenge to our understanding, a mystery waiting to be solved, a reminder that the universe is more complex than we often realize, and a testament to human curiosity and ingenuity. We found this structure, we measured it, we're trying to understand it. That's remarkable. Now let's dig deeper into something fascinating: the tools and technologies that allowed us to discover the Great Wall. Because finding something 10 billion light-years across required some of the most sophisticated instruments humanity has ever built. And understanding how we found it helps us appreciate just how far we've come as a species. Start with gamma-ray detection. Gamma rays are the most energetic form of electromagnetic radiation, higher energy than X-rays, higher energy than ultraviolet, higher energy than visible light, infrared, microwaves, or radio waves. A gamma-ray photon carries millions or billions of times more energy than a visible light photon. This makes them incredibly penetrating. They can pass through solid matter, through metal, through rock, through biological tissue. This is why gamma rays are dangerous to living things. They have enough energy to ionize atoms, to break chemical bonds, to damage DNA. Exposure to intense gamma radiation can kill cells, cause cancer, disrupt biological processes. But it's also why detecting them from space is so challenging. You need specialized detectors, materials that can absorb gamma rays and convert their energy into a signal you can measure. The first gamma ray detectors were simple: scintillation counters. A gamma ray hits a crystal. The crystal emits a flash of visible light. A photomultiplier tube detects that flash and creates an electrical signal. Count the flashes, and you know how many gamma rays you detected. But you don't know where they came from. Gamma rays don't refract like visible light. You can't focus them with lenses or mirrors. They pass straight through most materials. So early gamma-ray telescopes couldn't form images. They could only detect that gamma rays were arriving, not precisely where in the sky they originated. This changed with the development of coded aperture masks. Imagine a mask with a pattern of holes. Place it in front of your detector. Gamma rays pass through the holes and hit the detector. The pattern of hits on the detector depends on which direction the gamma rays came from. By analyzing the pattern, you can reconstruct the direction. It's like a pinhole camera, but for gamma rays. Multiple pinholes in a specific pattern. This technique allowed gamma-ray telescopes to locate sources in the sky, not with the precision of optical telescopes, but well enough to identify which part of the sky a burst came from. The Swift satellite, launched in 2004, uses coded aperture masks along with other techniques. It has a burst alert telescope that monitors the entire sky continuously. When it detects a gamma-ray burst, it determines the position within minutes, usually within 1 or 2 arc minutes. That's 1/30th to 1/60th of a degree. Still not pinpoint precision, but good enough to tell ground-based telescopes where to look. Swift also has X-ray and optical telescopes that can swing into position and observe the afterglow. The X-ray telescope provides a more precise position, down to a few arc seconds. The optical telescope can identify the host galaxy. This combination of instruments allows astronomers to detect a gamma-ray burst, locate it precisely, and study its afterglow, all within minutes to hours. This is remarkable when you consider that these bursts happen billions of light-years away. We detect an explosion that occurred when the universe was half its current age. We pinpoint its location in the sky. We identify which galaxy it occurred in. We measure the spectrum of that galaxy's light. We calculate its redshift and distance, all from a flash of gamma rays that lasted a few seconds. This requires not just sophisticated instruments, but also rapid communication networks. Swift is orbiting Earth. When it detects a burst, it transmits the coordinates to a network of ground-based telescopes. These telescopes are scattered around the world. Some are automated. When they receive the alert, they automatically slew to the coordinates and start observing. Within minutes, multiple telescopes are studying the afterglow, gathering data on its spectrum, its brightness, how it fades over time. This coordination is essential. Gamma-ray burst, afterglows fade quickly. Within hours, they might be too faint to study. You need to observe them fast. The global network of rapid response telescopes makes this possible. Now let's talk about measuring distances. Because knowing that a gamma-ray burst happened is one thing. Knowing how far away it happened is another. Distances in cosmology are determined by redshift. When light travels through an expanding universe, it gets stretched. The wavelength increases. For visible light, this shifts the color toward the red end of the spectrum, hence the term redshift. The amount of shift depends on how much the universe has expanded during the light's journey. More expansion means more shift. Greater redshift means greater distance. The relationship between redshift and distance is given by cosmological models. You measure the redshift, plug it into the model, and out comes the distance. But measuring redshift requires spectroscopy. You need to split the light into its component wavelengths. Look for specific features in the spectrum. Absorption lines or emission lines from known elements. Compare the wavelengths of these lines to their rest wavelengths measured in a laboratory. The difference tells you the redshift. For the Great Wall, astronomers measured the redshifts of the host galaxies of gamma-ray bursts. Each measurement requires careful observation. You need a large telescope to collect enough light from a distant, faint galaxy. You need a spectrograph to split that light into a spectrum. You need to identify specific spectral lines. Hydrogen, oxygen, calcium, other elements leave characteristic fingerprints in the spectrum. By measuring the wavelengths of these lines, you calculate the redshift. The gamma-ray bursts in the Great Wall have redshifts around 2. A redshift of 2 means the universe has expanded by a factor of 3 since the light was emitted. Wavelengths are 3 times longer than when the light left the galaxy. Plug this into cosmological models, and you get a distance of about 10 billion light-years. This process has been repeated for each gamma-ray burst in the sample, building up a 3-dimensional map. Each burst is a point in space, marked by its coordinates on the sky and its distance. Plot enough of these points and patterns emerge, clusters, filaments, voids, and occasionally, enormous structures like the Great Wall. Now let's think about the future. Because our ability to study structures like the Great Wall is improving. New telescopes are being built. New satellites are being launched. Our techniques are getting better. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire southern sky every few nights. It has a massive camera, 3.2 billion pixels, the largest digital camera ever built for astronomy. It will detect faint objects that current telescopes miss. It will catalogue billions of galaxies. It will measure their positions and brightnesses. Over the course of a decade, it will build the most detailed three-dimensional map of the universe ever created. With this data, we'll be able to see if structures like the Great Wall are rare anomalies or more common than we thought. We'll refine our statistical analyses. We'll test whether the Great Wall is really 10 billion light-years or if its size has been overestimated. We'll search for other large structures. Maybe we'll find larger ones. Maybe the Great Wall will lose its title as the largest known structure, or maybe it will remain unique, a genuine outlier in the distribution of cosmic structure. Either way, we'll learn something. Space-based missions are also improving our ability to study gamma-ray bursts. The Fermi Gamma-Ray Space Telescope has been operating since 2008. It has detected thousands of gamma-ray bursts. It has better sensitivity and better angular resolution than previous missions. Future missions will be even better. They'll detect fainter bursts. They'll locate them more precisely. They'll measure their energies more accurately. Each improvement gives us more data points, more gamma-ray bursts to map, better statistics, stronger evidence for structures like the Great Wall, or, potentially, evidence that the Great Wall isn't as significant as we thought. More data can go either way. It can strengthen a hypothesis or weaken it. That's what makes science exciting. You don't know what you'll find until you look. Now let's consider what the Great Wall tells us about the early universe. Because this structure exists 10 billion light-years away, which means it existed 10 billion years ago, only about 3.8 billion years after the Big Bang. The universe at that time was very different from today. It was smaller, denser, hotter. Galaxies were younger. Star formation was more vigorous. Galaxy mergers were more common. The gas between galaxies was ionized by intense ultraviolet radiation from young stars. This was the cosmic reionization era. For a few 100 million years after the Big Bang, the universe was too hot for atoms to form. Protons and electrons existed separately. The universe was opaque. Light couldn't travel far before being scattered by free electrons. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms. This happened about 380,000 years after the Big Bang. Suddenly, the universe became transparent. Light could travel freely. This is the light we see as the cosmic microwave background. For the next few 100 million years, the universe was dark. No stars had formed yet. The only light was the fading glow of the Big Bang, redshifted into the infrared. This is called the cosmic dark ages. Then, the first stars ignited. Massive, hot, short-lived stars. They emitted intense ultraviolet radiation. This radiation ionized the hydrogen around them, creating bubbles of ionized gas. As more stars formed, these bubbles grew and merged. Eventually, nearly all the hydrogen in the universe was ionized again. This reionization was complete by about 1 billion years after the Big Bang. The universe transitioned from neutral to ionized, from dark to lit by starlight. The Great Wall formed during or shortly after this era. It's a structure from the time when the universe was making its first galaxies, when structure formation was just getting started. This tells us that even in the early universe, matter could organize itself on very large scales. The seeds of structure, the density fluctuations from inflation, were already creating patterns. Dark matter was clumping together. Gas was falling into the dark matter halos. Galaxies were forming in those halos, and those galaxies were distributed across space in ways that reflected the underlying structure of dark matter. The Great Wall is a fossil from this era, a snapshot of how matter was distributed when the universe was young. By studying it, we can learn about the conditions in the early universe, the amplitude of density fluctuations, the behavior of dark matter, the rate of structure formation. All of this informs our models of cosmic evolution. It helps us understand how the universe went from a nearly uniform state just after the Big Bang to the complex web of structure we see today. Let's also think about what we can't see. Because when we observe the Great Wall, we're only seeing a small fraction of what's there. We see galaxies, bright concentrations of stars. We see quasars, active galactic nuclei outshining their host galaxies. We see gamma-ray bursts, explosions of individual stars. But we don't see most of the matter. Dark matter is invisible. It doesn't emit light. It doesn't absorb light. It doesn't interact electromagnetically at all. It only interacts through gravity, so we can't directly observe it. We infer its presence from its gravitational effects. Galaxies move in ways that require more mass than we can see. That unseen mass is dark matter. In fact, dark matter outweighs visible matter by about 5 to 1. For every kilogram of stars, gas, and planets, there are about 5 kilograms of dark matter. In the Great Wall, most of the mass is dark matter. The galaxies we see are just tracers, markers showing where the dark matter is concentrated. The true structure is invisible, a vast web of dark matter extending across 10 billion light-years. We can only see where visible matter has collected in the densest parts of this web. There's also dark energy, even more mysterious than dark matter. Dark energy doesn't clump, it's spread uniformly through space. It doesn't contribute to structures like the Great Wall. Instead, it drives the expansion of the universe, and it makes up about 68% of the total energy density of the universe. Dark matter is about 27%. Normal matter, the stuff we're made of, is only about 5%. This means 95% of the universe is dark, invisible, known only through indirect effects. We live in a universe dominated by things we don't understand. We can measure dark matter's gravitational influence. We can measure dark energy's effect on cosmic expansion, but we don't know what they are. We don't know what particles make up dark matter. We don't know what dark energy is or why it exists. These are some of the biggest questions in physics today. The Great Wall is part of this mystery. It's a structure shaped primarily by dark matter, held together by dark matter's gravity. Existing in a universe dominated by dark energy, understanding the Great Wall means understanding dark matter and dark energy. And we're not there yet. We're making progress. Experiments are searching for dark matter particles, deep underground detectors waiting for a dark matter particle to collide with an atomic nucleus, particle accelerators trying to create dark matter in collisions, telescopes mapping the distribution of dark matter through gravitational lensing. Cosmologists are studying dark energy by measuring the expansion history of the universe, looking at distant supernovas to see how fast the universe was expanding at different times, measuring the cosmic microwave background to constrain dark energy's properties, surveying millions of galaxies to map how structure has grown over time. Each of these efforts contributes to our understanding. Slowly, piece by piece, we're learning about the dark components of the universe. The Great Wall is one piece of this puzzle, a structure so large that it pushes the boundaries of our theories, a challenge that might point us toward new physics. Now let me share something that might put all of this in perspective. The Great Wall is 10 billion light-years across. But what does that really mean in terms of the universe as a whole? The observable universe is about 93 billion light-years in diameter. That's how far light could have traveled since the Big Bang, accounting for expansion. It's the limit of what we can possibly see. Beyond this, light hasn't had time to reach us yet. The Great Wall spans about 10 billion light-years. That's roughly 1/9 the diameter of the observable universe. Imagine the observable universe as a sphere. The Great Wall stretches across about 11% of that sphere. It's not the whole universe, but it's a significant fraction of everything we can observe. Now consider this. The observable universe might not be the whole universe. It's just the part we can see. The actual universe might be much larger, possibly infinite. If it's infinite, then the Great Wall, as large as it is infinitesimally small compared to the whole. An infinite universe would contain infinite structures, infinite galaxies, infinite great walls, infinite copies of every possible configuration of matter. This is speculative, of course. We can't observe beyond the observable universe, but it's worth considering. Even the largest structure we know might be tiny in the context of the full universe. This raises interesting philosophical questions. What does it mean for something to be large? Large compared to what? The Great Wall is enormous compared to Earth, compared to the solar system, compared to the Milky Way, even compared to most cosmic structures. But if the universe is infinite, the Great Wall is infinitely small. A point, basically. So size is relative. It depends on your frame of reference. From a human perspective, the Great Wall is incomprehensibly large. From a universal perspective, it might be insignificant. Both perspectives are valid. Both tell us something true about reality. Let's think about time again, because the Great Wall exists in time as well as space. We see it as it was 10 billion years ago, but it's still there now, presumably, in some form. What's happening to it right now, in the present moment? We can't know for sure. Light takes time to travel. Any information about the current state of the Great Wall won't reach us for 10 billion years. By then, our sun will be long dead, Earth will be gone. Humanity will either have moved to other star systems or cease to exist. But we can make educated guesses. The structure is probably still there. 10 billion years isn't long enough for a structure this large to dissipate completely. Galaxies within it are still orbiting, still evolving. Some have merged with neighbors. Some have drifted farther apart. Star formation continues in some galaxies. In others, it has slowed or stopped as gas supplies run out. Black holes at the centers of galaxies continue to grow, slowly accreting matter. Occasionally, two galaxies merge and their central black holes eventually merge too, creating gravitational waves that ripple through space-time. The overall structure persists, not frozen, but changing slowly, evolving over billions of years. In another 10 billion years, the Great Wall will look different. Some galaxies will have moved. Some will have merged. The overall distribution will have shifted, but the large-scale structure will likely remain recognizable unless cosmic expansion tears it apart, which, eventually, it will. In the far future, all structures will dissolve as space expands faster than gravity can pull matter together. But that's trillions of years away. For now, the Great Wall exists, a massive structure spanning 10 billion light-years. Now let me tell you about the human stories behind this discovery, because science isn't just about data and theories. It's also about people. Astronomers who dedicate their careers to understanding the cosmos. Istvan Horvath, the lead researcher who identified the Great Wall, spent years analyzing gamma-ray burst data. This isn't glamorous work. It's painstaking. Carefully extracting positions and redshifts, building databases, running statistical tests, checking and rechecking results. Most scientific work is like this. Patient, methodical, detail-oriented, not the dramatic eureka moments portrayed in movies. Horvath and his colleagues didn't set out to find the largest structure in the universe. They were studying the distribution of gamma-ray bursts, trying to understand if these events are clustered or randomly distributed. The Great Wall emerged from their analysis, an unexpected pattern in the data. At first, they were probably skeptical. Statistical flukes are common. You find patterns that aren't real. You see correlations that disappear when you gather more data. So they tested it, ran different statistical tests, checked for systematic errors, looked for alternative explanations, and the pattern held. The concentration of gamma-ray bursts was significant, too significant to ignore. They published their findings in 2013. The paper presented the evidence and acknowledged the implications. If real, this structure violated theoretical predictions about the maximum size of cosmic structures. It challenged the cosmological principle. The paper was cautious. They didn't claim to have definitively proven the existence of a 10 billion light-year structure. They presented evidence and invited the scientific community to scrutinize it. This is how science works. You publish your findings. Other scientists examine them. They try to replicate your results. They look for flaws in your methodology. They test alternative hypotheses. Over time, the community reaches a consensus. Either the finding holds up or it doesn't. In the case of the Great Wall, follow-up studies have generally supported the original finding. The concentration of gamma-ray bursts remains significant. Additional data from quasars suggests a real overdensity of matter in that region. But the debate continues. Some astronomers remain skeptical. They argue the statistical significance might be overstated. They suggest the structure might not be as coherent as it appears. This is healthy. Science benefits from skepticism. It keeps researchers honest. It prevents premature conclusions. It ensures that extraordinary claims are backed by extraordinary evidence. Over the coming years, more data will accumulate. Better telescopes will provide more precise measurements. New surveys will catalogue more gamma-ray bursts and quasars. The Great Wall will either become more firmly established as real, or it will fade as additional data dilutes the apparent clustering. Either outcome teaches us something. If it's real, we learn that the universe can create structures larger than we thought possible. If it's not, we learn about the pitfalls of statistical analysis with small sample sizes. Both are valuable lessons. Behind this scientific process are real people, researchers spending long nights at telescopes, analyzing data on computers, writing papers, attending conferences, debating interpretations. They're driven by curiosity, a desire to understand how the universe works, not for profit or fame. Most astronomers aren't famous. Most work in relative obscurity. Their discoveries matter to a small community of specialists, but they continue because the work is meaningful to them, because understanding the cosmos is its own reward. This is one of the beautiful things about science. It's a collective human endeavor. Thousands of people across generations working toward a common goal, understanding reality. Each contribution is small. Each individual discovery is a tiny piece of a vast puzzle, but together they add up to something remarkable. A comprehensive understanding of the universe, from the smallest particles to the largest structures. The Great Wall is one piece of this puzzle, found through the efforts of many people. Astronomers who built the satellites, engineers who designed the detectors, programmers who wrote the data analysis software, theorists who developed the statistical methods, all contributing to this one discovery. And this is just one structure, one finding among millions. Science is filled with these stories. People working together, often without even knowing each other, to advance human knowledge. It's inspiring when you think about it. Now let's come back to the question that started this journey. What is the largest object we've ever found in the universe? The answer, based on current evidence, is the Hercules Corona Borealis Great Wall, a structure spanning 10 billion light-years, a concentration of galaxies, gas, and dark matter, an anomaly that challenges our theories of cosmic structure formation, but this answer comes with caveats. We might be wrong about its size. Future observations might revise the measurement. We might find larger structures. The universe might contain things we haven't discovered yet. Science is always provisional. Our best current answer based on available evidence, subject to revision as we learn more. This doesn't make the answer less valuable. It makes it more honest. We're not claiming absolute truth. We're presenting the best understanding we've achieved so far. And that understanding is remarkable. We've mapped structures across billions of light-years. We've detected events from the early universe. We've measured distances that light takes 10 billion years to cross. We've used mathematics to understand cosmic evolution. We've built instruments sensitive enough to detect faint flashes from across the universe. All of this represents an extraordinary achievement for a species that evolved on one small planet, a species that has only been doing modern science for a few centuries. In the grand scheme of cosmic history, we've barely existed. Humans have been around for maybe 300,000 years, civilization for about 10,000 years, modern science for about 400 years. The universe is 13.8 billion years old. We've been studying it for a tiny fraction of its existence. And yet, in that brief time, we've learned an enormous amount. We've figured out that the universe is expanding. We've measured its age. We've mapped its large-scale structure. We've discovered dark matter and dark energy. We've detected gravitational waves. We've found thousands of planets around other stars. We've traced the history of cosmic evolution from the Big Bang to the present. And we've found structures like the Great Wall. Objects so large, they span a significant fraction of the observable universe. This is what humans can do when we apply ourselves, when we build on each generation's knowledge, when we work together toward common goals. It's easy to focus on humanity's problems, on our conflicts and failures, on the ways we fall short of our ideals. And those problems are real and important. But it's also worth recognizing our achievements. The Great Wall is one of them. Not because we built it, we didn't. It formed billions of years before Earth existed, but because we found it, because we developed the tools and methods to detect a structure 10 billion light-years away, because we had the curiosity to ask questions and the persistence to search for answers. That's worth celebrating. So as we close out tonight's journey, remember this: the universe is vast beyond comprehension. It contains structures so large, they challenge our understanding. The Hercules Corona Borealis Great Wall, 10 billion light-years across, is the largest we've found. But we're small, confined to one planet, at least for now, limited by the speed of light and the vast distances between stars. And yet, despite our limitations, we can reach out with our telescopes and our mathematics. We can detect and measure and understand things far beyond our physical reach. We're made of atoms from ancient stars. We're participants in the ongoing cosmic story. And we're the part of the universe that can look back and understand its own history. That makes us significant. Not because we're large or powerful, but because we're aware, because we can comprehend beauty and complexity, because we can wonder at the majesty of a structure 10 billion light-years across, and because we can share that wonder with each other. Thank you for spending this time exploring the cosmos with me. If you found this journey worthwhile, a like or subscribe helps this channel continue bringing you these deep dives into the universe. The Great Wall exists, spanning distances that light takes billions of years to cross. And we, tiny as we are, have discovered it. That's something to marvel at. Before we finish, I want to leave you with one more thought. One more layer to this story that brings everything together. The Great Wall isn't just about size. It's not just about breaking records or finding the biggest thing. It's about what that discovery means for us as a species and for our future. Think about where we started as humans. For most of human history, we believed Earth was the center of everything. The sun, moon, planets, and stars all revolved around us. This made intuitive sense. Earth feels stationary beneath our feet. The sky appears to rotate around us. Ancient civilizations built entire cosmologies based on this Earth-centered view. The Greek astronomer Ptolemy created detailed mathematical models in the 2nd century. His geocentric model could predict planetary positions with reasonable accuracy. It dominated Western thought for 1400 years, but it was wrong. In the 1500s, Copernicus proposed that Earth orbits the Sun, not the other way around. This was radical. It displaced humanity from the center of the cosmos. It suggested we're not special, not the focal point around which everything else revolves, just one planet among others. Galileo's telescopic observations in the early 1600s supported this. He saw moons orbiting Jupiter, proof that not everything circles Earth. He saw phases of Venus, evidence that Venus orbits the Sun. The heliocentric model gradually gained acceptance. Humanity took its first step down from the cosmic pedestal. We're not at the center. The Sun is, but that was just the beginning. In the early 1900s, astronomers discovered that the Milky Way is a galaxy, a vast collection of hundreds of billions of stars. Our Sun is just one star among countless others, not at the center of the galaxy, not particularly special, just an ordinary star in an ordinary location. Then Edwin Hubble discovered in the 1920s that the fuzzy nebulae visible through telescopes weren't gas clouds in our galaxy. They were other galaxies, entire separate islands of stars, billions of them scattered throughout space. The Milky Way wasn't the whole universe. It was one galaxy among multitudes. Another step down, we're not in the center galaxy. We're in one galaxy among billions. Hubble also discovered that these galaxies are moving away from us. The universe is expanding. This led to the Big Bang theory, the understanding that the universe had a beginning, that it started in an incredibly hot, dense state and has been expanding and cooling ever since. We're not in a static, eternal cosmos. We're in a universe with a history, a universe that changes over time. Throughout this journey, each discovery has displaced humanity from any privileged position. We're not at the center of the solar system, not at the center of the galaxy, not in a special galaxy, not in a static, eternal universe. This process is sometimes called the Copernican principle, the idea that we don't occupy a special place in the cosmos, that Earth, the Sun, the Milky Way, none of them are privileged or central. We're typical, ordinary, part of a vast, ancient universe that would look roughly the same from any other vantage point. The cosmological principle extends this idea. It states that on large scales, the universe is homogeneous and isotropic, the same everywhere and in all directions. No location is special. No direction is preferred. This principle has been remarkably successful. It underlies our models of cosmic evolution. It explains why the cosmic microwave background is so uniform. It's consistent with nearly all observations. But the Great Wall challenges this. A structure 10 billion light-years across suggests that maybe the universe isn't as uniform as we thought. Maybe there are variations on scales larger than the cosmological principle allows. Maybe our location in the universe can see structures that other locations can't. Maybe we are, in some sense, in a special place, not because we're at the center. The universe has no center, but because we happen to be positioned where we can observe this enormous structure from a different location in the universe, you might not see it. You might see different structures. The distribution of matter might look different. This doesn't mean we're returning to a geocentric worldview. We're not claiming Earth is at the center of everything, but it does suggest that the Copernican principle might have limits. That while we're not in a special location in any absolute sense, different locations in the universe might have genuinely different large-scale environments. This is philosophically interesting. It raises questions about how we understand our place in the cosmos. Are we typical observers in a typical location, or are there aspects of our cosmic neighborhood that are unusual? The Great Wall suggests the latter might be true, at least on the very largest scales. Now think about what this means for the search for extraterrestrial life. If the universe isn't perfectly uniform, if different regions have different concentrations of matter, different rates of galaxy formation, different environments, then the probability of life might vary across the cosmos. Maybe some regions are more conducive to life than others. Maybe regions with higher galaxy density have more planets, more opportunities for life to emerge. Or maybe the opposite is true. Maybe denser regions have more supernovas, more gamma-ray bursts, more radiation, making them more dangerous for life. We don't know. But the Great Wall suggests that the universe is more heterogeneous than we thought, and that heterogeneity might have implications for where and how often life emerges. Consider also the future of astronomy. Every generation has access to observations that previous generations couldn't make. Galileo saw moons around Jupiter, something invisible to the naked eye. Hubble saw other galaxies, something earlier telescopes couldn't resolve clearly. Modern telescopes detect gamma-ray bursts from billions of light-years away, something impossible before space-based instruments. Each technological advance opens new windows on the universe. We discover things we didn't know existed. The Great Wall was discovered with gamma-ray satellites and sophisticated statistical analysis. Without these tools, we'd have no idea it exists. What will future generations discover? What structures or phenomena are we currently unable to detect? The universe might contain things larger than the Great Wall, things we can't observe because we don't have the right instruments yet, or things that don't emit radiation we can detect. Dark matter structures, for instance. We infer dark matter from its gravitational effects, but we can't see it directly. There might be vast structures of dark matter that don't have visible matter associated with them. Pure dark matter filaments, or halos, invisible to our current telescopes, but real and massive nonetheless. Future technologies might allow us to map dark matter directly, maybe through improved gravitational lensing studies, maybe through new types of detectors. When that happens, we might discover that the Great Wall is just the tip of the iceberg, that there are even larger structures we simply can't see yet. This is the nature of science. Each answer raises new questions. Each discovery reveals how much we don't know. The Great Wall is a perfect example. We found it, but we don't fully understand it. We measured it, but we're not certain of its exact size or nature. We published papers about it, but the debate continues. This might seem frustrating. Why can't we just figure it out definitively? But this is actually how science progresses. Through ongoing investigation, debate, refinement. We don't expect to solve everything immediately. We expect each generation to advance our understanding a little further, to ask better questions, to gather better data, to develop better theories. The Great Wall will be studied for decades to come, maybe centuries. Each study will add a little more clarity. Future astronomers will look back at our early 21st century observations the way we look back at early 20th century astronomy, crude by their standards, limited by the technology of the time, but valuable nonetheless. First steps toward deeper understanding. Now let's think about scale one more time from a different perspective. The Great Wall spans 10 billion light-years. To put that in context, the Milky Way galaxy is about 100,000 light-years across. The Great Wall is 100,000 times larger than our entire galaxy. If the Milky Way were the size of a coin, the Great Wall would stretch over half a mile. Our entire galaxy, with its hundreds of billions of stars, reduced to something you could hold between your fingers. And this structure would extend over 3,000 feet away from that coin. The Laniakea supercluster, which contains our galaxy and about 100,000 others, spans about 520 million light-years. The Great Wall is roughly 20 times larger than Laniakea. 20 structures, each containing 100,000 galaxies, each galaxy containing hundreds of billions of stars. That's the scale we're dealing with. You are unimaginably small compared to this, made of about 7 octillion atoms, each atom mostly empty space. You're on Earth, a planet 7,900 miles in diameter. Earth orbits a star in a galaxy 100,000 light-years across. That galaxy is part of structures that pale in comparison to the Great Wall, and yet you can understand all of this. You can comprehend the Great Wall even though you'll never see it directly. Your mind can span from atoms to superclusters, can think about the smallest particles and the largest structures, can understand that everything is connected through the laws of physics. This is extraordinary. Your brain is about 1.4 kilograms, made of about 86 billion neurons, creating a network that gives rise to consciousness, to thought, to the ability to understand the universe. No other structure in the known universe can do this. Stars are massive and powerful, but they're not conscious. Galaxies are enormous and complex, but they don't think. The Great Wall is the largest structure we've found, but it doesn't know it exists. Only you do. Only conscious observers can understand the cosmos. And as far as we know, conscious observers are rare. We've found thousands of planets around other stars, but no signs of life yet. No alien civilizations broadcasting radio signals. No evidence of advanced technology in other star systems. This might mean we're alone, or effectively alone, because other civilizations are too far away to ever communicate with us. If that's true, then we're the only part of this region of the universe that can understand itself. The only minds that can contemplate the Great Wall. The only consciousness that can marvel at cosmic structure. That's a profound responsibility. It means we need to survive, to continue learning, to pass our knowledge to future generations. Because if we disappear, this region of the universe loses its only window of self-awareness. This gives our existence significance, not because we're large or powerful, but because we're aware, because we can appreciate what exists. Because we can find beauty in a structure 10 billion light-years across. Because we can understand our own origins as stardust organized into conscious beings. This is what makes us special in the universe. And it's why discoveries like the Great Wall matter, not just as scientific facts, but as reminders of our place in the cosmic story. We're small, but we're significant. We're temporary, but we're conscious. We're fragile, but we're capable of understanding things far greater than ourselves. The Hercules Corona Borealis Great Wall, 10 billion light-years across, the largest known structure in the observable universe, a challenge to our theories, a mystery waiting to be fully understood, and a testament to human curiosity and ingenuity. We found it. We measured it. We're trying to understand it. And in doing so, We're fulfilling our role as the universe's way of knowing itself. Thank you for joining me on this journey across cosmic scales. If this exploration expanded your sense of wonder, a like or subscribe would mean a lot. It helps this channel continue bringing these deep dives into the mysteries of the universe. Remember, we live in a universe of unimaginable size and complexity. A universe with structures that span billions of light years. A universe that created stars, galaxies, planets, and ultimately, us. We're part of something far greater than ourselves, and we have the privilege of being able to understand it. That's worth celebrating. Good night. And may you never look at the night sky the same way again.